pleasure to have Henry, who's going to talk about experimental design.
Right, thank you very much. Yeah, great to be here. I've got a little bit of a ambitious title. I think it would be ambitious even if I had a long time to talk about it, but I've only got 30 minutes, so I'm going to probably fall short on 2 counts here. But I'm very much interested in experimental design, like a lot of you guys are. But I'm also interested in how can we use cool generative models that are sort of popping up all the time to do that. So obviously there are loads of cool models now that can generate complicated scientific structures like molecules, proteins, this sort of thing. So it feels like they should be really useful for designing experiments. But perhaps it's been quite ad hoc so far. I'm trying to think a little bit more about how you should tie these sort of systems together. So how do you tie kind of mathematical experimental design and also generative AI? Okay, so generative AI is really cool. There's loads of cool examples. It's in the news all the time. Obviously, all you guys, you know that the coolest type of generative AI is the generative probabilistic modeling, like Gaussian processes. But what I'm actually going to talk about is more this sort of thing. So how do I combine Gaussian processes with models that can generate really cool structures? Okay, so I was desperate to get this picture in, these 3D planes. But one of the applications I'm going to talk about is plane design. So doing some engineering design. I've got a generative model that can essentially generate unlimited amounts of valid-looking planes. How can I use this though in experimental design? And so the main thing that I'm interested in are these things called highly structured spaces. So this is not a clear definition, but I'm interested in problems where it's very hard to write down exactly what the structure of the space is or what the constraints of the space are. Okay. So I say this got a constraint which is you know it when you see it. Okay. So this is not a plane, right? For sure. This is a plane on the right. Okay. But it's very hard for me to write down a formula, either write it down in closed form or even learn from data. The function, is this a plane, right? This thing on the right here, clearly a plane. The one on the left is not, but I can't write it down in a nice way where I can be able to optimize it. So the actual structures here are 3D meshes. So I've got sort of several thousand points in 3D space. And I'm interested in moving these around in a way that I can design a plane that's optimal with respect to some objective function. This is the context for all of what I'm going to talk about. So I don't have time to really go into the details of any of these generative models, but they always look a bit like this. So you could apply the sort of methods that I'm interested in to VAEs, to diffusion models, to normalizing flows, any of these sort of models. But they all look roughly like this if you squint a bit. The idea is that you have this sort of fancy neural network bit in the middle that maps samples from a really nice, easy distribution to some very structured output. Okay, so these are the sort of models I'm interested in. A very common example is molecule spaces. Okay, so this is a kind of a popular VAE setup here, where you can sample randomly from a high-dimensional Gaussian distribution, some neural network magic happens, and you end up with something that looks quite like a valid molecule. Okay, so there's some very complicated things going on in the middle, but we're able to kind of generate at will from this distribution, P of x. Okay. How do I go back? There we go. So I'm interested in Bayesian optimization. So we've kind of touched this a little bit over the last few days, but it's sort of sequential experimental design where we have a Gaussian process for our unobserved objective function. Right? So I'm interested in maximizing objective function. Typically there's some sort of constraint. Okay, so the idea is, can I find the optimal value of my objective function that lies within a certain region? Okay, so I'd be looking for kind of this sort of star here within this constrained region here. There's loads of kind of very powerful methods to do this. We've spoken about some of them so far. But I'm interested in this sort of quite kind of strange setting here where I'm interested in maybe maximizing a function, so an objective function, over some very structured space x, where my constraint here is somewhat related to my generative model. Right? So I want to be able to find a point that gives me a very high objective function. So it's going to score high according to f of x, but it also is deemed to be very likely according to my generative model. Okay, so I want to find the x's so that my generative model, so p of x, is relatively high, right? So you can imagine having some sort of arbitrary threshold. This would give you an optimization problem that you could kind of write down, right? I'm trying to maximize a function given some constraint. Unfortunately, this is really, really difficult, right? We had the picture of the plane before. I can make a tiny change to my plane, right? I move 1 pixel and it's suddenly not a plane anymore. So that's what I'm trying to kind of pictorially show here, is that the constraint set here is impossible. It's essentially impossible to optimize directly in the space that we're interested in. So we have these horrible constraints. There's also a small subtlety in that this guy, often I can't actually even evaluate that. For some of these generative models I can, But for many of them, all I can do is sample from P of X. So that's problematic. So we can't just apply kind of standard Bayesian optimization or standard optimization algorithms directly to this problem. So that's what I'm kind of focusing on in my research at the moment. So this is a very common setting that people are interested in, this idea of trying to use the Z. Okay, so there's this thing called latent space optimization, which is where you go back to this nice picture here. And what people do is they say, okay, it's very hard for me to kind of navigate this space, really, really difficult to do this. So what instead I'm going to do is map back into this space and move around in this space, because this is continuous, hopefully. It's probably going to be quite high dimensional still, which is a problem, but it will be continuous. So if I move around in here, this is smooth, I can apply a standard optimization routine that works in the Euclidean space. Okay, so that's kind of a nice setting to be in. And this is kind of fundamentally a bad idea in my books. This is an abridged version of the talk. Normally I have about half an hour now where I just really rude about using structured spaces via this latent space. But I've only got one slide version of that instead that's going to be on the next slide. But the key idea of these latent space optimization methods, one example of this would be latent space Bayesian optimization, is that you use your search space as the latent space. Oh, sorry. I use my latent space as my search space, so I just define my optimization in the latent space. And I also have a surrogate model now, or objective function, whatever it might be, that actually maps from my latent space to my output. Okay, so normally I'm really rude about the second point, but I don't have time to do it. So I'm just going to be rude about the first point very quickly. There's this issue with these generative models. So this is a kind of in the context of VAEs, but this is true for all generative models that have Gaussian latent spaces, is that actually we've got quite high dimensional spaces. One of the examples I'll show you in a bit, I've got 10,000 dimensions Gaussian distribution. And actually all the samples from that Gaussian have this particular property that they concentrate on this very thin shell that's quite far away from the origin. Okay, so this is a very common idea to anyone that's done kind of high dimensional statistics, but we seem to have missed it in machine learning for quite a while. But what people do instead is they go, okay, right, search space is unbounded, let's just focus on a very central region of this search space to do my optimization in. So that's kind of completely at odds with this idea that I've trained a model that can map Gaussian samples into good molecules if I'm just going to focus on this central region, right? This is a really big problem. So this is a very clear, if you're just going to optimize in your latent space and treat it as a Euclidean space, that's a bad idea, basically. You might think, okay, I'm going to be clever, I'm going to maybe define my Gaussian process or my surrogate model to only make sense on that shell. You might think, oh, I'll map into high-dimensional spherical coordinates. You know, you can imagine doing this sort of stuff, and maybe that's a good idea, but I couldn't be bothered. So instead, I really kind of thought very carefully about how I'm actually using this model. So I wanted to think about, okay, I'm only ever going to use the VAE or the generative model in the way that it's been trained to be used in the context of my optimization problems. Cool. So this is the setting. The idea is that these GenAI models are built for sampling from, but we've got to be careful if we're going to try and do anything else with them. Imagine I'm doing an experimental design loop here where I'm trying to generate kind of some, for example, molecules here that satisfy a certain condition, and I want to do a sequential sort of loop like we've discussed already today. What I might do is, for my initial design, so my first set of experiments, I just sample from my generative model. Okay, that seems like a completely reasonable thing to do, and that's also a very safe thing to do. Like, my model has been trained to be able to do this. So I can sample from my generative model, that's great. And then I might think, what shall I do for my subsequent steps? Okay, once I have a bit more information about what's going on. So I have my objective function, so f of x. I'll have, for example, a Gaussian process that's trying to predict what that objective function will be. And then what I'd want to do on my subsequent steps is sample from this model in a way that meant that the samples I got were both highly likely according to my generative model, but also likely according to some sort of Bayesian optimization criterion, right? So that's what we've got up here. So I will unravel this a little bit now because it's a bit complicated. But the idea here is that this is a conditional generative model. So I'm conditioning on this kind of slightly weird looking condition here. But then what this condition means is that my Gaussian process here, so f of x, and my predictions at this new molecule x, I think they're going to be bigger than some particular threshold that I have in mind at the moment. Okay. So if I'm able to sample from this bottom guy, I'm getting things that are both highly likely according to my generative model, but also kind of quite likely according to my GP. Okay. And if you're familiar with Bayes opt, you'll recognize this as something somewhat similar to probability of improvement, which is a very common idea. So this is how I'm proposing tying these two sort of systems together. So before we were talking about variational autoencoders and fitting models inside their latent spaces. I'm not doing any of that. Here I have basically a generative model, and then I'm just going to do some sort of careful sampling from it, conditional sampling. And that conditioning statement is how my sort of discriminative model is coming in, the thing that's going to predict how good molecules are, for example. The key thing here is that I'm never doing any optimization within each of these steps. Right? I'm not optimizing an acquisition function. I'm not doing anything like this. I'm still just sampling. I'm just doing constrained sampling. One way to get intuition for what I mean for this would be to think of, suppose I'm kind of 10 steps into my optimization. I could fit my Gaussian process to those 10 steps. So now it's giving me an idea about what other molecules might be promising. And I could just generate a ginormous number from my generative model. And I could throw away all the ones that don't satisfy this predictions from my model. Okay. So that's one way you could do it, but it's really data inefficient. For most of the problems I'm interested in, this condition rules out the vast majority of the molecules you might want to generate. So you have to start to think about how do you actually do this conditional sampling from these generative models. And this can be very model dependent, but this is what I'm spending a lot of my time at the moment doing. But I have kind of this sort of quite text-heavy slide that sort of summarizes how the field is doing this. But this idea of conditioning the generative models, some people are kind of training these, ooh, spoilers, training these from scratch at each step. Okay, so you can imagine I've got some new data coming in, maybe I've trained my diffusion model from scratch again. That's kind of a bad idea, it's very expensive. There are some clever methods where people are doing kind of little bits of fine-tuning of these generative models. There's model-specific approaches, so there's like guidance approaches that people like as well, if you're familiar with those. For the rest of this talk, I'm going to focus on a really terrible idea that I had and still managed to get a paper out on MCMC. And then I'm going to talk a bit more about a slightly more involved method to play around with the latents. And I'm hoping to get, I've got a video of a cat at the end that comes out of this approach, which is kind of fun. But I had to add this slide in. So have everyone heard of Jamiroquai? I don't know how big it is in Europe. Have you, David? Yeah? I gave this talk in the US and I got even more cold response than that. But anyway, so I have a paper where we're using this approach basically, Return of the Latent Space Cowboys, and we have an algorithm that almost gives you cowboys. Seems to be acceptable within the machine learning community to do this sort of thing. I know David's not a massive fan of this, but anyway. I'm not going to go into the details really. It's exactly what I described on the previous slides, basically. The paper is there if you want to, or email me. But I wanted to very quickly give you a feel for why the approach that I proposed is interesting. So this is a very common setting. You see these plots, they're kind of boring Bayesian optimization plots called regret plots. But the idea is that we have some objective function. This is a molecule-based objective function. And I'm trying to find a molecule with a really high score as quickly as I can. Right? So this is the number of molecules that I'm evaluating. And if you use the standard approaches, these latent space Bayesian optimization approaches, you kind of get performance that looks a bit like this. Okay? So these ones are finding decent things after a long time. If you instead use the sort of framework that I described, where you don't fit models in latent spaces, and you instead do some kind of conditional sampling, the way I do conditional sampling in this paper is horribly slow, and this does not scale at all. But it gives you a flavor for why I'm interested in these approaches. And you see that we get kind of dramatically superior optimization here. So this was a really compelling result, and this is something that we're focusing on a lot at the moment, is scaling this up to bigger problems. Okay. So I said, we've got the MCMC. This is something that I'm building on a lot, so how do we do conditional sampling with the GenAI models? I'm now, for the rest of this, going to focus on this last one, which is a bit more fun. But the idea is, how do we kind of control the outputs of these generative models in quite a straightforward way? And this work is kind of embarrassingly simple, in a way. There's not going to be any complicated maths in here. But it works, which is nice. So it's always nice when you get something like that. Here we are. So this is the picture I showed you before. We're in exactly the same setting. I have very sneakily changed the word probabilistic to deterministic here. So for this work, we are exclusively interested in things where there is a deterministic mapping between your Gaussian inputs and your highly structured output, right? So Gaussian noise to molecule or to image or whatever. And that does sound very restrictive, but it turns out actually for most of the models I'm interested in, the diffusion, the flow matching, there are typically tricks to do this. There are kind of different ways of reformulating the problem. You can apply some kind of reparameterization tricks and things to allow this to happen. So let's just assume that I now have a deterministic mapping from my latent space to my molecules, okay? which is nice. And then the idea would be, okay, suppose I found a molecule I'm really interested in. It would make sense to kind of find out where that goes to in this space, make a small change in this space, and then we'll end up with more molecules that are somewhat similar to the molecule I had at the start. Right? That's a very natural thing to try and do. I've already kind of slagged off those sort of methods. I've already said, okay, if we go into the latent space, we can't just move around in that space, so we have to be somewhat careful. So in this work, we're interested in how can we control what we're getting out of this model by controlling the latent space. So we've got some very simple ideas, and they all kind of hinge around this idea that you should never evaluate this model in a way that it's not been trained to be used. Okay? So we should never be trying to evaluate samples right in the middle of this distribution, for example. We should always be evaluating Zs that are somewhat likely according to a Gaussian distribution. Okay, so my notations had to change a little bit, which is a bit frustrating, but we've got Zs, Xs, and Ys coming up now, and they all mean something different to what they meant before. But this is the setting. The idea is that I have a load of Xs here. So these Xs are going to be the latent space locations of some things that I'm interested in. Okay? Imagine I've got 5 molecules I'm interested in, or 5 images that I've generated. You can imagine mapping them back into their latent space. So these Xs here are their latent encodings. And then what I might want to do, and this does sound very simple and restrictive at this point, is just make linear combinations of those guys to get a new latent location and then push that back through my model to see what I get out. Okay? So this is a kind of a manipulation I might want to do in my latent space. Right? Just linear manipulation. So it sounds very sort of limiting, but actually a lot of things fall into this framework. For example, if I want to interpolate between 2 locations in my latent space, that's just a linear operation. I might want to find centroids, so averages of molecules or images or something. That's a manipulation that would work here. But the one we really care about is this idea of actually, suppose that I have, say, 5 molecules I'm interested in. Can I make a subspace? Okay, can I make a 5-dimensional subspace that basically spans those molecules, where everything in that subspace is going to map to a valid molecule on the way out? Okay, so that's kind of hard to say in words, but you'll see in a picture in a second what I mean. So we're all based around this simple idea of making sure that we never give the model something that it's not been trained to deal with. So those of you eagle eyes, you'll notice that if I have, say, these guys, which are, say, Gaussian samples, all right, because they've come from valid molecules, if I make just a linear combination of those, this resulting thing is no longer Gaussian normal zero identity, right? It's no longer a symmetric Gaussian. So that's a problem. And there's lots of kind of very complicated work in the literature where they're trying to kind of map these things in certain ways, and there's very complicated methods. Some of them involve actually optimizing the network again. But we had a very sort of straightforward idea, which was, let's just find the optimal sort of transport map from this guy back onto the Gaussian that we care about. Okay? So we did this from quite a mathematical perspective. The paper itself, we've got kind of a lot of mathematical motivation for this. But what you end up with is incredibly simple, and actually is kind of a nicer place to start with the explanation. But the idea is that I've generated this y here, okay? Oh, my typesetting's gone off a bit, oh well. I've generated this y that's not going to be the right sort of Gaussian. All I need to do is divide through by this scaling factor, which is given by the sum of the squared weights, and you end up with the higher dimensional Gaussian again. Okay, so this is a super simple kind of warping. It does it's quite a complicated warping. When we kind of analysed it, it is quite hard to understand, but it's at least simple to write down. But this is really, really straightforward. The idea is that we can now, given some inputs, I can make some linear combination of them, and I know how to kind of adapt them to put them back through my model. Okay, really, really straightforward idea. And I think hopefully the pictures will be helpful. Okay, so this is Stable Diffusion, so one of the most popular image generating models. Okay, and what I've done is I've got these, say, 5 images that I'm really interested in. I'm not actually interested in these guys, but this is the setup. These 5 kind of fancy cars, and what I wanted to do was build a spanning sort of subspace between these 5 cars. So if I just made like a standard subspace, so just a subspace made by like the linear combination of the latents for these 5 guys, if I take a 2D slice of that, I get complete garbage basically, because I'm leaving this Gaussian manifold. So I end up with either complete crap, so just nothing coming out of the model, or like really poor diversity, right? These are very poor samples. If we use our very simple approach that just requires essentially rescaling everything by a constant, you can get these sort of subspaces out, okay? So this is a fun example as well. So here we've got kind of these, the original latents, like this one here is kind of manifesting up here, but we're getting kind of a good interpolation. So I'll say exactly what this is one more time. So we've got these 5 input images. I've made a 5-dimensional space that spans those images. So it's just 5 dimensions rather than the sort of 10,000 you would have normally for these models, such that this is a nice 2D slice. These are 2 different 2D slices of this, which is fun. So we can now navigate. We've got a 5-dimensional space we can navigate that gives us all sort of images that are like the ones that we gave to it, which is fun. Obviously, this is kind of a stupid application that we don't really care about. But what we did care about was this setting. So here we have a model that can generate 3D structures, okay, so these meshes that I showed you earlier on. And I want to then have this model and really focus its generations into promising areas of the space. And then we'll be able to do optimization with it. So this is the idea, is that I've generated a load of planes from my 3D plane model, and I've picked basically 3 basis functions. So I've decided that according to my problem, I'm interested in this plane, I'm interested in this plane, and I'm interested in this plane. What I can then do is use the approach I've described to make a 3-dimensional subspace that every point in that subspace maps back to a valid plane. So according to my generative model, and I can here, this is just a 2D slice, right? So you see that this guy is present down here, and this one is present up here. So this is a 2D slice. And then to try and motivate why we might care about this space that we've generated, on the right here, I've plotted the log wave drag. So this is just a kind of quite a toy problem still, but this is an objective function you might be interested in when you're designing planes, for example. So I've calculated that using expensive numerical simulations for each one of these 3D plane designs, right? And you see that there is structure in here that for sure our optimizer could now exploit, right? So we've turned what was, the original problem here would be to, okay, find a plane that has low log wave drag, right? That would be very hard. I'd be optimizing this sort of 10,000 dimensional structure. Be very, very difficult. We've turned that into a problem now where it's just a 3-dimensional optimization problem, right? Where we don't have any constraints at all. So this is really powerful, and it's really nice. Got a few more minutes. We'll be doing the same thing for kind of some protein design problems. So this really powerful diffusion model, RF diffusion, that generates proteins. It struggles when you try and get it to generate very long proteins. So we thought that was an interesting sort of area to try and explore in terms of experimental design. Could we get this model to generate very long proteins that were somewhat synthesizable? And we have this we're following some of the literature, we have this terrible way of deciding if a protein is realistic or not, which is we get our protein generated by our model, so that's the light color here. We then push it through another series of machine learning models which try and recreate that protein. And the idea is that if these proteins are well aligned, so if the dark color is similar to the light color, then it's a realistic protein. Okay, this is a proxy, a very, very bad proxy for in-lab suitability of the molecule. Now that's the setting. So the idea is, can we somehow generate a very long protein from this model using experimental design? This takes a little bit of unpacking, this picture here, but the idea here in the background, this blue, that is this residual, so the difference between the generated protein and the regenerated protein, so a proxy for synthesizability. The orange one here, is what happens if you just use the standard model. Okay, so no experimental design, no controlling of the latent space, you're just generating. And you see that all of these guys, so we did it 100 times, none of them are very realistic, right? We're not exploring the space properly, we're focusing on the wrong sort of proteins. Whereas for our approach here, what we did was we sampled 25, we picked the best 5 as our basis functions, and then spent the rest of our evaluation resources in the span of those 5 promising proteins. We get this sort of blue distribution here. So we are finding a couple that are below this threshold in a way that the original model couldn't do. Okay. The same thing is explained there, but that's not exciting. What's exciting is the picture. So you see that we get on the bottom row here, so our top 10 solutions, this is the 1st, the 5th, and the 10th best solutions in terms of this sort of metric and reconstruction loss, are all kind of much better than the ones you get from random design, which is just using the model as it was trained to do. We are losing a bit of diversity, and that's something that we're interested in thinking about in these problems. We've got the paper up if people are interested in looking at this. I like to leave on, well, actually I've got one more for this audience, but I do like to leave on this funny picture of interpolating between a duck and a boat. So you've got to be careful when you use these models, very careful. But my final example, this is the first time I've showed this actually. So we used, this was a couple of weeks ago, we used a very popular image generation diffusion model. I wanted to have a nice kind of subspace like I showed you before, but this is a completely contrived setting where I'm saying, oh, imagine I've got two videos that are really promising. How do I explore the space of videos between them that are still valid? And this is what we did here. So here we've got two cat videos that we're interested in. I'll show you one more time. So we've got the one on the top left and the one on the bottom right. And using our approach, we're able to get these sort of, like, what the videos in between, right? We haven't got an application for people that want to optimize videos, but I think this is really cool. I do also have some horrible audio samples down the left, but I'm not going to inflict those on you because I'm running out of time. I'll show you one more time. I thought this was fun. It's a nice visual way. Yeah, but I've not seen anyone optimize over videos before, so I think we're onto something here. Just need to find an application. But yeah, I'll leave it at that. Thank you.
Questions now?
With a very applied mind, where do you see this kind of method, where do you see the place of this versus, I guess, human intuition design? Like, take this to a designer of planes, they intuitively, sort of, they know kind of what's going to be good or not. Where would you see your methods fitting in their process?
That was actually kind of the idea for this, was we're actually pretending that the generative model is the human intuition to some extent. The purpose of this project was to try and like inject this sort of structural information that plane designers have, right? They can look at the weird blobby thing I had and be like, that's not a plane. And the way we did that was by getting this huge sort of corpus of historical plane designs and training this model on them, which took a lot of work. That's meant to be trying to embed their knowledge essentially through, kind of that's the process in like an automatic way. It's not quite the same thing, but that was the idea. How can we use like vast historical sort of records, you know, maybe they're historical plane designs, maybe they're just like molecules we made over the last few years, for example. How do we use that information to accelerate optimization? And I think that this is one of the ways you could do that.
Hi, thank you for the great talk. So I was interested in the quality you need from the generative model, because if you map between, I mean, latent and, I mean, whatever, targeted degrees of freedom, how crucial is it that your model is, let's say, trained perfectly?
What do you mean by trained perfectly? Like, these things are always a bit iffy, to be honest. Like these models, the ones I've trained you are quite good, I guess. You want to be able to, I guess your question is related to, is the optimizer within the support of the generative model and the mismatch there. So I think that's interesting. We've always kind of assumed that our generative models are capable of producing the thing, you know, the optima, essentially. And that's certainly the case, I think, for like the image models and things, you know. It's very hard to find an image that they can't map back through and map back again. And for these models, we're definitely in the situation that you described. And these models are not as strong. So I guess there is tension there. At no point are we kind of suggesting that we actually are getting full optimization here, right? These tasks are impossible, right? We're never going to find the optimal plane design. We're trying to find like a solution that's somewhat similar to what people have already done. You know, sort of a halfway solution, I guess. Yeah.
Okay, yeah. So there are many approaches to do edition in a latent space. Okay, and what I have understood is that here you have chosen to have data with a certain property to train your generative AI. But did you study also cases where you have it's a more complex operation than
the linear combination. Yeah. That's what we're doing at the moment, essentially. Yeah. This was, you know, it does feel somewhat limiting, but then even these simple like operations do seem to get you quite far with what you want to do. There are lots of much more interesting things you might want to do, and it's a case of we're doing kind of a lot of optimal transport stuff to try and work out exactly, you know, maybe I do some crazy operation of these latents and I end up in something very, very different. How do I work out how to take that back to the manifold that we're interested in? So that's what we're doing at the moment. There's a lot more interesting stuff with kind of discrete diffusion models where the prior distribution is now kind of discrete and there's more complicated things going on. And that's exactly the setting that I think you described. Things become much harder, and yeah, we're kind of exploring that at the moment.
Thank you for the question.
I have one very simple question about your weights.
Oh, yeah.
So do you choose them non-negative or do you allow them to be?
They can be anything. They can be positive or negative. When we're doing these search problems, we're building these the subspaces. We are forcing the subspaces to be kind of in the, I guess, the positive kind of orthant of that space.
For the moment, you're...
Yeah. Because if you think about what's going on here, it's kind of, each direction here is somewhat to do with like how much the plane is going to be.
Yeah.
So you can imagine if you went the negative way, you'd be saying, oh, I want to have less of an effect of that guy. And this is what we're trying, when I said I'm struggling with diversity a bit, we actually are throwing in like bad examples in our basis to get that sort of...
So in that case, the right structure is a convex hull.
Yeah. But actually, what we're doing now as well is, you might imagine doing this where you have these three basis planes that are very promising, and you might find one that's even better when you're doing a search. So should you add that into your basis, or should you take one out? You know, there's all these sort of questions about how you should proceed in an iterative way here. So it's using a lot of results from kind of subspace optimization literature and that sort of thing, with these sort of dynamic sort of basis.
And have you seen in some applications negative weights that were bringing some improvements?
Yes, there was some. If you had a really terrible example, like a plane that was really, really rubbish that you definitely didn't want to have in there, some properties that you didn't want, then having that in the basis was kind of helpful in terms of building a search space that included the thing you were interested in.
All right.
Thank you.
Okay, thank you very much. So, thank you.